rational function is a function such that we have two polynomials, one on top and one on bottom. Remember, a polynomial can be degree 0 through degree whatever. So it could be a particular number, which is a degree 0 polynomial, or it could be like an x squared or something like that on the top. But there has to be an x on the bottom for it to be a rational function. It is also very important that we notice that the g of x function cannot equal 0. G of x is the one that's on the denominator. So we're going to have restrictions on the domain, or restrictions on the input values we can use for these functions, which we will discuss later on. Today, what we're going to be focusing on is their end behavior. So if you remember, we ended the last section of Unit 1, Part 1, with end behavior of polynomials, where we did like the arms thing, and you had to write me some limit statements. We're going to be doing the same thing, but for this type of function today. The end behavior of a rational function is determined by the leading terms of the numerator and the leading term of the denominator. So if we're just thinking about this again, we're thinking about the numerator and the denominator. We just want the leading terms, which means we want the largest exponent and we want the leading coefficient that goes with it. Okay, case number 1, and these cases have fun names in my class and in this class. Okay, case number 1, we're going to call Bobo. What? Yes, B-O-B-O, but that second O is actually a 0. So a Bobo case means that the denominator has a bigger degree than the numerator, aka it is bigger on bottom. That's the B-O-B, bigger on bottom. If it's bigger on bottom, then the horizontal asymptote for this graph is 0, which is what that second 0 is trying to tell you. If it's bigger on bottom, meaning the degree is bigger on bottom, the horizontal asymptote is the line 0. So horizontal line at 0. And since a horizontal line is what's going to happen all the way across at the ends of the graphs, that also tells me the end behavior of this function. And so we can write them as limit statements. We would say that the limit as x approaches negative infinity for the function, we'll call it f of x, is equal to 0. We also know that that same end behavior happens on the other side. So the limit as x approaches positive infinity for f of x will still be 0. We're using the same number literally everywhere. The number you use and identify as the horizontal asymptote is the number that you use in your limit statements for both sides. I'm going to skip case 2 for a second. We're going to talk about case 3. In case 3, this is called the Betsy case, which is B-E-T-C. So for B-E-T-C, Betsy, if you will, the bottom degree is equal to the top degree. Bottom equal top. If this is the case, then the function has a horizontal asymptote at the fraction a over b. Now, where did we get this a over b from? That is a great question. If you notice on your paper, there's an a over b in this polynomial, in the rational function, meaning you took the leading coefficient of the numerator and the leading coefficient of the denominator, and you just divide them. But just like with the Bobo part, whatever number you get as the horizontal asymptote is the number we use in our limit statement to describe end behavior. So we'd say the limit as x approaches negative infinity for a function f of x would be that value a over b, whatever you got. The limit as x approaches positive infinity for f of x is equal to a over b as well. Whatever that number is, you just repeat it for both the left side end behavior and the right side end behavior. So if you're like, Miss Quickly, but why Betsy? C stands for coefficients. So you're dividing the coefficients. Betsy. Case number 2. Its acronym is called BOTN, B-O-T-N. And I skipped this one because this type of function does not have a horizontal asymptote. And that's what the N stands for. It stands for none. None. So it does not have a horizontal asymptote. But what's going to happen here is because it doesn't have a horizontal asymptote, it's going to have different end behavior. And that end behavior is going to match A polynomial with the properties of a leading coefficient of a over b and a degree of n minus d, meaning the degree of the numerator's degree minus the denominator's degree. So this is the one where we'll have to pause for a second, and we'll have to write limit statements that go off to one of the infinities. So it will be either positive or negative infinity on the left side, and be either positive or negative infinity on the right side. So Bobo and Betsy's are actually the easier ones, quote unquote. Botten graphs are going to be a little bit more challenging. And I know it says a little note right there. I'm skipping it on purpose. I'm going to read it towards the end of this page. So let's just practice for a second, recognizing if our function is Bobo, Botten, or Betsy. So we are going to pay attention to the degree of the numerator and the degree of the denominator. So if we look at example 1, part A, we're going to determine if it has a horizontal asymptote and then write the equation of the asymptotes. We're not even talking about end behavior just yet. What is the degree of the numerator? 2. What is the degree of the denominator? So those are the same number, yes? So this is a Betsy graph because the bottom is equal to the top. Betsy tells me that I'm going to take the leading coefficient or the leading term and take the coefficient of both the top and the bottom and divide them. What is 3 divided by 5? Can't actually do it, so we leave it as the fraction 3/5. So we would say that this function has a horizontal asymptote at the line y equal to 3 over 5. If we were writing the end behavior statements, both the limit going to the left and the limit going to the right would be equal to that number 3 over 5. Let's look at number B. For the numerator, what is the degree? I heard 2 and 1. Remember, degree is the largest exponent. What's the largest exponent showing in the numerator? 1. What's the largest exponent in the denominator? 2. So where is it bigger? On the bottom. Bigger on bottom is Bobo. And remember, Bobo is not actually 2 O's. That second O is a 0, which tells me that the horizontal asymptote is going to be y equal to 0. Let's look at letter C together. For letter C, what is the degree of the numerator? What's the degree of the denominator?
1.
So where is it bigger?
Numerator.
On numerator, so bigger on top. That's the case that's called Botten. This is bigger on top. The N stands for no horizontal asymptote, so that's literally what you write. You would say that there is no horizontal asymptote. So the question here is it Bobo, Botten, Betsy? And if it's Bobo or Betsy, tell me the horizontal asymptote. I want you guys to try examples D, E, and F. You're writing down whether it's Bobo, Botten, or Betsy and identifying the horizontal asymptote. Okay, if I'm cutting off your thinking, I'm so sorry. But for letter D, is that one Bobo, Botten, or Betsy? Betsy. The degree on the top is 1. The degree on the bottom is 1, which means we're going to divide the coefficients. Now, the coefficients here are 4 and 8. What is 4 divided by 8? 1/2. So my horizontal asymptote is at y equal to 1 over 2. If you put 4 over 8, not wrong, but please reduce fractions at all times. That's 1/2. For the second equation, what's the degree of the numerator? Is there even an x at all? Yeah, so it's degree 0. So we have degree 0 on top. What's the degree of the bottom? 2. So this one's bigger on bottom. That means it's a Bobo equation. So what is the horizontal asymptote for a Bobo? 0. So we'll say the horizontal asymptote is y equal to 0. Fabulous. How about the last one, Bobo, Botten, or Betsy?
Bobo.
Still Bobo. Yeah, this one's still Bobo. So since Bobo ends in a 0, we know that the horizontal asymptote here is y equal to 0. Now there's something interesting that should happen at letter C. So I'm going to go back to that one now that we've gotten the idea of Bobo, Botan, and Betsy. When you're looking at a Botan graph, we're going to have to do a second to be like, something interesting's happening here. What's the degree of the numerator again on C?
2.
And what's the degree of the denominator?
1.
So what's the difference between those things?
It's just 2.
Yes.
Well, 2 on top, 1 on bottom. It's bigger on top by how many? 1. So I'm actually going to change the way we write this. It is Botan, but it is specifically bigger on top by 1, correct? When it's bigger on top, specifically by 1, no, it doesn't have a horizontal asymptote. But this very particular type of graph that's bigger on top by 1 is going to have something called a slant asymptote. So while we say no to the horizontal asymptote, we're going to say yes to a slant asymptote. A slant asymptote is one that kind of looks like a linear function where it's maybe like positive on one side and negative on the other. It's slanted. So we have this third option that's like a caveat to our Botan graphs. And it even says this in this note. If the degree of the numerator is exactly 1 more than the degree of the denominator, then f of x has a slant or oblique asymptote. Remember, that is specifically for when it is bigger on top by 1. So Botan by 1, if you will. Still no horizontal asymptote, so the end still works. But if you notice it's specifically bigger on top by 1, you'll say no to the horizontal asymptote, but yes to the slant asymptote. If it's bigger on top by 2, no to both. If it's bigger on top by 3, no to both. Only a slant asymptote when it's bigger on top by 1. So if we're writing now the limit statements that describe end behavior, for rational functions, you still want to focus on those horizontal asymptotes. For this graph of k, do you see the like dashed line representing the horizontal asymptote right here? Do we see that line, right? Okay. If you don't, it's this guy right here. Do you see how on this graph, as we extend to the right and we extend to the left, the lines are both kind of flattening out, air quotes flattening out, on this dashed line? This is what a horizontal asymptote looks like. It's a line that the graph is going to get close to but never touch horizontally. But horizontal asymptotes, because they go this direction, do describe our end behavior. So for both sides, on both ends, aka, what is the horizontal asymptote? 2. So as I go this way towards negative infinity, what is the graph getting closer to? And as I go to positive infinity, what is the graph getting closer to? So our end behavior, our limit statements, we know are going to that horizontal asymptote of 2. We would say the limit as x approaches negative infinity for this function k of x, negative infinity, right, on the left side, going to 2. The limit as x approaches positive infinity for k of x is also equal to 2. Because on the left side, we're flattening out at the horizontal asymptote, and on the right side, we're flattening out at the horizontal asymptote. Flattening out is air quotes. It's not actually getting flat, but it's getting very, very minutely close to that horizontal asymptote. Since this is a number right here, we put the number 2. Would this equation be Bobo, Botan, or Betsy?
Wait, repeat it again?
This is Betsy because we have a number. The C stands for coefficient, so we have a number. Let's write that down because that's helpful to remember. This is some sort of Betsy question, Betsy equation, because we had a number that we were going towards. Okay, let's do the same thing for M. So can we identify where the horizontal asymptotes are? There's only one. Negative 1. Don't be fooled by the vertical asymptotes there. We'll get to those later. The horizontal asymptote is going to help us find the end behavior. On either side, what is the graph flattening out at? Negative 1. So we know that we can write the limit statements. The limit as x approaches negative infinity for m of x would be equal to that number, negative 1. And the limit as x approaches positive infinity of m of x, is equal to also negative 1. Either direction, we're getting closer to that horizontal asymptote. Would this graph be Bobo, Botan, or Betsy? Betsy again, because why? They're equal, they're the same number, so we have a horizontal asymptote. The only reason it would be Bobo is if that number is 0. If we have a number other than 0, it's Betsy. Okay, so this last one is a little bit different. This is still a rational function. It doesn't have the dashed line showing for you, But do you see how we don't have a horizontal asymptote? If we were to draw one in, it would be an asymptote that kind of goes like this. In this, shall we say, slanted direction. This is what a slant asymptote might look like. It's slanted, but the graph still on its ends on the left side and right side is going towards that asymptote. We can use the slant asymptote to still write the end behavior. So if we're looking at this graph, as we go off this way, and if it keeps going and going and going and going, where is it kind of heading towards? Negative infinity. So we can say for this graph that as x, that's not even the word limit, that's just L-I-N. Limit as x approaches negative infinity for j of x would be equal to negative infinity because it's going down. It's following the slant asymptote. What would be happening as x approaches positive infinity? It's going up because it's following that slant asymptote. This side's going to positive infinity. Would this rational function be Bobo, Botten, or Betsy? Botten, and specifically, it would be Botten by how many? By 1. Because we have that slant asymptote that it's following, this is going to be specifically Botten by 1. We don't have the equation written here because all we have is the graphical representation, but we know that this would be some sort of Botten by 1 because it has a slant asymptote that we could have drawn in there. Okay, so that's like level easy because I gave you the graphs of what it looked like so we could write the end behavior. If we step it up another level, when I give you the equations themselves, we just kind of have to do like what you guys did on that Kahoot just now and ask ourselves, is this Bobo, Botten, or Betsy? So let's hear it. Is this Bobo, Botten, or Betsy? Betsy. So Betsy means that we're going to divide the coefficients. I'm going to go ahead and write that down because that's helpful for me to see on my notes specifically that this is Betsy. Betsy also tells me that I'm going to divide the coefficients of the leading terms. Typically, they're the first terms. Make sure you don't fall for a trick like that. So if we are writing this one, its horizontal asymptote would be 2 over 6, which is 1/3. That also means that the limit statements, as we go to negative infinity for f of x, would also be 2 over 6, which is 1/3. And the limit as we go towards positive infinity for this f of x would again be 1/3. Are we following? Yes. Okay. So if we're following, I know I write faster than you, so I'm going to slow down. For the second one, if you're asked for end behavior, and it's a rational function, you first think Bobo, Botten, or Betsy. What is this one? Bobo. Now Bobo, we have to remember what that means. Bobo, it's bigger on bottom, which means the horizontal asymptote is 0, which also means that the end behavior on both sides goes to 0. So we can write the limit statements right away. The limit as x approaches negative infinity, this time for g of x, is equal to 0. And the limit as x approaches positive infinity for g of x is equal to 0. Okay, so this next one is a bit of a doozy. So if we look at letter F, what kind of rational function is it? Bobo, Botten, or Betsy? Botten. Any more details on that Botten? It's Botten by 1, which means we're going to have a slant asymptote, which means just like the graph above it, our limit statements are going to go off to one of the infinities. Our job now is not just to say no horizontal asymptote. We actually have to figure out what that slant asymptote would look like so that we can write the limit statements. The way that this would work is we think for a second over here. I'm just going to draw a sidebar. Our end behavior matches a graph that would be y equal to negative 3 over 1 times x to the 4 minus 3. What? Good question. Let me write down. Let me show you what I'm doing here. The end behavior, our slant asymptote, is going to match the behavior of a polynomial function if I take the leading coefficients and divide them. Leading coefficient of the top is negative 3. Leading coefficient of the bottom is 1. And subtract the degrees. What's the degree of the top?
4.
What's the degree of the bottom? Okay, so let's make this look nicer because, ew. If we were to actually simplify this, this would become negative 3 and x to the first power. If we jump back to when we learned about polynomials, is this even or odd as a polynomial? The degree, is it even or odd? Odd, because it's degree 1. Okay, so should your arms be going the opposite or the same direction? Opposite. Now, which way should your right hand be going if this is -3? Down. So it's going to look like this. Our end behavior is going to look something like this. That would be what our slant asymptote looks like because it matches the behavior of a graph that has those qualities. And if you're like, how am I going to remember that, Miss Quigley? It's actually printed on the front side of your paper in the bottom section. So you don't have to remember that. It's already printed for you on your notes. So if we have this shape for our slant asymptote, this shape for our end behavior, we can write our limit statements. The limit as x approaches -infinity for h of x, what should I write down? Positive or negative infinity? Positive, because the left side goes up. And the limit as x approaches positive infinity for h of x is equal to -infinity. We're following the behavior of that slant asymptote. We're following the behavior of the function as if it was a polynomial, which is back in section 1.6. Now, all this that we just did is kind of re-emphasized in this little box here because we've talked about the slant asymptotes. This gives it its own thing. There's a lot of math happening in this, but let me highlight the important parts for you. Slant asymptotes occur in a graph that is bigger on top by 1, and only when it's bigger on top by 1. We got that earlier in the Kahoot. We're good. But what's going to happen is the slant asymptote is going to be parallel to the line that has a very similar end behavior to the line that we just set up here. So if I'm looking here, this line that we say we are parallel to, so this is not the actual equation of the slant asymptote, but this is the behavior of the slant asymptote. This is what we did here. We took the same behavior and we used it to write our end behavior statements. This is the behavior of the slant asymptote at the end. In a further lesson from now, we're going to actually find the equation of these slant asymptotes, but we're just figuring out now the lines it would be parallel to. So let's see what this would look like in like a multiple choice scenario situation. So AP style question. An AP style question when it comes to slant asymptotes may ask you, which of the following rational functions has a slant asymptote that is parallel to the line 1/2 x? Well, we know two things. We know that slant asymptotes only occur in botten by 1. So let's first try to eliminate some answer choices by seeing which ones are not botten by 1. How would you classify this graph? Botten by 1. Okay, so we actually keep that one. Not that exciting. Botten by 1. Okay, what about the second one? It's bigger on bottom. So can that one have a slant asymptote at all? Nah, goodbye. Bobos do not have slant asymptotes. They have horizontal asymptotes at 0. What about number 3? What kind of function is that one? Botten by 1? Okay, cool. What about the fourth one? By 2. Do bottens by 2 have slant asymptotes? No, just botten by 1. So look, I already have it down to 2 answer choices that's possible. All we need to do is think about the behavior of the slant asymptote. The behavior of the slant asymptote is going to come from those leading coefficients here and here. If this one has the same behavior, it would be parallel to the line y equal to 3/2x. Number 3, what would it be parallel to? Y equal to 1/2x. So which one actually answers the question that we want here? The third one. This is the one that actually has that correct behavior for my slant asymptote being parallel to 1/2 x. So it kind of feels like you're doing the like Betsy thing, right? And it does. It does kind of feel like the Betsy, and that definitely helps you eliminate answer choices when it comes to slant asymptotes, because finding the actual slant asymptote is kind of annoying because it requires long division of polynomials. Let's try to eliminate answer choices the best way we can.